All right. Well, good morning, everybody. Thanks for taking the time to watch the screencast with me. So guys, today what we're going to do is we're going to take all the information that we learned last time as we took the Bohr model of the atom and finally put it to rest and then came back and started to pick up some of the building blocks that we need to replace the Bohr model. What we're going to do is we are now going to take that information that you gathered last time in class, and we are going to reorganize it. We're going to structure it a little bit differently, and what we're going to find is that by doing that, the direction that we've been headed for the last few weeks, thinking about getting to the place where all of these interesting shapes and pictures that are over on the east side of the classroom with all the clover leaves and the spheres and all these different pictures, we're finally going to get to the point where some of this begins to make sense. We're going to finish this conversation next time in class, but we are going to take that first step, and along the way we're going to talk about some extra credit. But guys, in order to be ready for today, what you're going to need to do, as it says on the screen, you are going to need to get your class notes from last time. Those class notes include some information about Heisenberg and the idea of probability, and then the table that allowed us to transition from the Bohr to the Schrodinger model of the atom. And then down at the bottom there was an outline that included things with energy levels and sublevels and orbitals, and then the concept of spin. That's where we're going to be today. So even if you want to take that notes page and fold it in half, you won't be referencing the things about Heisenberg or probability. We'll simply be looking at the bottom. So guys, the way that today is then going to go is we are going to start by making sure that you have at quick reference the information that we're going to need out of last time's class notes. Then what we're going to do from there is we're going to introduce a conceptual idea called a core sample, and I'll show you more about that in just a second. And then guys, at that point, we are going to begin to take the information from last time and organize it into a model that more closely represents all the stuff that's up on the wall. So in order to do this, as we mentioned, you're going to need your class notes from last time. But you're also going to need the class notes page from today, which is the one that says the wave mechanical model across the top. So with this said, let's go ahead and get started by making sure that you have in your notes everything that you need to know from last time. So guys, looking at last time's notes, you'll notice that first of all, we had the energy level quantum number n. And we talked about the idea that the energy level is, let's do this in red, that is the size of the cloud. And guys, I would encourage you to highlight, maybe even circle these things in your class notes so that they're more quickly accessible. So the quantum number n, the energy level number, tells us the size. We also know that it has values from 1 to 7. On our periodic table. And then guys, finally, we know that the capacity of an energy level is given by the 2n squared rule. So these are the important things that you need to understand relative to the energy levels. The energy level tells us the size. There are 7 different sized energy levels, and the capacity is given by the 2n squared rule. Okay, then energy levels are broken into sublevels. Sublevels are the next breakdown below energy levels. So energy levels broken into sublevels, and there's a limited number of sublevels in each energy level. So the number of sublevels in an energy level is given by n. You may remember from the homework that we did last time, the first energy level has 1 sublevel, that's an S. The second has 2, S and P. The third has 3, SPD. The fourth has 4, SPD and F, which then leads us back to the idea that there are 4 different types of sublevels, and those are S and P and D and F. If that's not coming back to you immediately, you might want to pause the video and then go look at your homework assignment number 1 from last time. And on the back of that, you'll notice that there's a table that says energy levels and then the sub-levels that are in them, and that'll be a good reference for you. Okay, moving along then, sublevels are broken into orbitals. Now remember that orbitals are actually the clouds. They are the space that is occupied by up to 2 electrons. Could be 1, could be up to 2, no more than that. But the orbitals are actually the clouds, the spaces that electrons appear to occupy. Remember the idea that within that space they can be anywhere, and therefore they behave like they're everywhere. We talked about that relative to the idea of the fan blades, that the fan blades are not everywhere, but they behave like they're everywhere because they are, well, moving through space, whereas electrons are popping in and out of existence. But that's the idea behind the orbitals or the clouds. Then finally, the orbitals, again, contain 2 electrons, but the tricky bit is that these electrons, it's difficult for them to pair up because they're all negative. And the way that the electrons can pair is that electrons have magnetic poles, a north pole and a south pole, and when they come together, they orient themselves so that one electron will be north pole up. We call that spin up. And then the other one will be spin down, and that's where we get the ideas of spin up and spin down electrons. Okay, so there we have it. These are the things that we need to know about energy levels broken into sublevels, sublevels broken into orbitals, and then these orbitals, the cloud-like structures, contain 1 or up to 2 electrons, and if there are 2, then these electrons are understood to one be north pole up and the other north pole down. Okay, so guys, again, these are all going to be really important resources for us as we move forward. Before, though, we move forward, the next thing we need to do is we need to orient ourselves to the handout, the notes page for today. So guys, the first thing that you'll need to do is draw a half circle around the abbreviation nucleus in the bottom left-hand corner. And then, guys, if you would, draw in this little squiggly equal sign. And guys, for those of you that don't know, that little squiggly equal sign means something is missing from the graph. And the thing that's missing here is a whole lot of space. Remember the idea that if the nucleus is the size of a marble, then the electrons are in the cheap seats of a football stadium. Now, guys, understand that our nucleus is way bigger than a marble, which means that our electrons will be much, much further away. But obviously, if we drew this to scale, then the places where we find electrons would be very, very, very far away. And that just wouldn't be reasonable. So understand this is not to scale, and the electrons are not that close to the nucleus. Okay, then moving across to the top, we need to label these. We have the energy level, the sublevel, and the orbital. Now, remember the idea here, guys, that energy levels are broken into sublevels. Sublevels are broken into orbitals. And so what we're going to do is this is where we're going to represent information about the energy levels. This is where we're going to represent sublevels, S, P, D, and F. And then this is where we are going to represent the information about the orbitals. So energy levels broken into sublevels, sublevels broken into orbitals. Okay. So now that we're up to speed with that, we need to really understand exactly what it is we're looking at when we look at this model, if you will, of an atom. So in order to do this, you need to understand the idea of a core sample. Now, if you've never taken apples and turned them into applesauce or something like that, you've probably never used an apple corer. But an apple corer is actually a hollow metal tube with jagged teeth on the end And what you can do is actually insert that jagged metal tube. It's down over the stem of the apple, and you can literally pull the core out of the apple, and the core is then inside the corer, and you can pull it out, and basically it allows you to peer inside of an apple. Well, if we do that, but if we go to the middle and not all the way through the apple, and then if we then pull this out, we can learn some interesting things about the inside of an apple. We see that the apple has a core, and then above the core, the apple has flesh, and it has a stem, and it has skin, and we can see what is on the inside of an apple by using a core. Well, we can do something like that to an atom. And notice what we've got. We've got the cloud of the first energy level. We've got the cloud of the second energy level. We've got the cloud of the third energy level. And if we were to then take a core of this atom, notice then what we would have. We would have the core, or the nucleus of the atom, and then we would have a rung here, and then we would have a rung here, and then we would have a rung here, and those rungs would just continue to build up. But understand, these rungs represent the boundary of the size of each one of these clouds. So if you understand that, now peer back at your class notes for today, and hopefully you see the connection as we work our way over here. So hopefully you're seeing the connection that what we have here is we have the nucleus, and then we have the boundary of the first cloud, the boundary of the second, the boundary of the third, and the boundary of the fourth. So literally what we're looking here is at the energy levels where those simple little rungs represent the boundaries on these energy levels. Okay, so guys, at this point, now that you understand what we're looking at, and now that you understand core samples, and now from our class notes from last time, we've got energy levels broken into sublevels, sublevels broken into orbitals, and those orbitals containing electrons that have opposite spins. Guys, we are now ready to fill out this better model of the atom. But guys, understand that in doing this, all I need to do now is start to ask you questions. And I'm going to do it that way. And I'm going to go slow enough that you would have the opportunity to find these answers in your notes from last time. So guys, here's what we've got. We've got 1, 2, 3, 4 energy levels. But guys, from our notes from last time, we know that those energy levels don't stop at 4. How high do they go? And guys, if you look back at your class notes, you'll notice that the energy levels do not go 1 through 4, they go 1 through 7. So we are going to label them 1 and 2 and 3 and 4, and then we're going to acknowledge that they go up to 7. Even though we're not going to list all 7 of the energy levels. Okay, so now we need to know how many electrons are in these energy levels. And so, referring back to your notes, there is an equation that allows us to calculate how many electrons are in each of these energy levels. That equation is the 2n squared rule. And so by applying the 2n squared rule, we know that we have 2 electrons in the first energy level, then 2 squared is 4, double that is 8 electrons in the second, 3 squared is 9, times 2 is 18 electrons in the third, and then finally 4 squared is 16 times 2 is 32 electrons in the fourth energy level. So this could go up to 7, but we're not going to do that. We're going to stop at 4. So now we've identified the number of electrons in the first 4 energy levels. Now what we're going to do is we are going to move to the right, and we're going to start talking about the sublevels that make up these energy levels. So here we go. Looking down at energy level 1, draw an arrow that allows your eye to see that we are now moving over to sublevels. And again, guys, all of the answers to all of these questions are in your class notes from last time. So the question is this: how many sublevels are in the first energy level? And if you remember, we talked about this previously. There is one sublevel in the first energy level, and it is an S sublevel. So what we're going to do, and this is just a way to make a placeholder, we're going to draw a line underneath sublevel. And we are going to allow this line to represent the S sublevel in the first energy level. So we are going to label that 1S. So now what we've got to do is we've got to figure out how many electrons are in that sublevel. So allow me to share an analogy with you that might help you figure this out. So imagine that a farmer, like in Pleasant Grove, decides that he's ready to sell his family orchard, and they're going to turn it into neighborhoods. So this rectangle represents the neighborhood that was once an orchard. And of course what they do is they then build a street in that neighborhood. Now, what if there were 2 houses in that neighborhood? So if there's 2 houses in the neighborhood, how many houses have to be on this street if there's no other streets in the neighborhood? And obviously the answer is 2. If there are 2 houses in the neighborhood, and if there's only one street, then both of those houses have got to be on that street because, how do you like my houses? There's no other place to build the houses. Well, guys, the same logic applies here. We have a neighborhood like an energy level, and that neighborhood only has one street. So if that neighborhood only has one street, then both of the houses have to be on the street, or in this case, both of these electrons have got to be in that sublevel, and so that sublevel contains 2 electrons. That might have been a stretch, but this logic will repeat, and we'll come back to it, and it'll make more sense. Now, we're going to move right again, and we're now going to talk about orbitals. So referring back to your class notes, how many electrons go in an orbital? And if you go back and look, you'll notice that there are 2 electrons in an orbital, and we'll talk later, but those 2 electrons have opposite spins. So we have now established that 2 electrons go in an orbital. So now the question is this: if we have 2 electrons in this sublevel, how many orbitals do we need in order to house those 2 electrons? So if an orbital can hold 2 electrons, and if we need space for 2 electrons, then we only need 1 orbital, and that orbital looks like this. So now what we need to do is we need to draw this. So before we draw it, let's explain, exactly what it is that we're looking at here. Okay. Now let's zoom in again. So what is it that we're looking, there we go. What is it that we're looking at? And what we have here is an up and down axis, a side to side axis, and an in and out axis. And if you're not familiar with that, that is 3-dimensional. So when we draw a circle on top of that 3-dimensional axis, what we're actually drawing is a sphere. So go ahead and do that. Draw your up, down, left, right, and diagonal in and out axes. and then draw a sphere on top of that, indicating that that is the one orbital that is in the 1s sublevel, and it's a sphere. So now, guys, pause for a second and look around the room. See if you can find something in the room that represents that small spherical orbital in the 1s sublevel. And guys, just to keep things simple, and there's dozens of examples of these in the room, but if you look in the front left corner where we have the yellows, the greens, the grays, and the browns hanging off the wall there, that upper left-hand small yellow sphere is the sphere that you just drew onto your class notes. That small yellow sphere is the orbital in the 1s sublevel. Okay, so now that we've done that, we are now ready to move up to the second energy level. Now, guys, as we move up to the second energy level, we now need to ask ourselves how many sublevels are in the second energy level. So we said that the first has 1, it's an S. The second has 2, and it is S and P. So what we're going to do is we are going to draw this arrow, drawing our eye to the right, and then we're going to draw 2 lines. Now notice where this goes. This is important. If you draw an imaginary line from the second energy level, this line goes below it, and this line goes above it. And then when we label these, we call this the 2S and the 2P. Second energy level has an S and a P, but in the second energy level, that would be the 2S and the 2P. Okay, so now what we need to do is we need to figure out how many electrons are in these sublevels. So without knowing it, we established a rule. S sublevels contain 2 electrons. So there's also 2 electrons in the 2s. Now the question is, how many electrons have got to be in the 2p? And I suspect that you probably see that the answer is 6. If we have 2 electrons here, and we need 8 electrons total, then there's got to be 6 electrons in the 2p. Okay, so now we are ready to move over to orbitals. So the question then becomes, how many orbitals do we need to house the 2 electrons in the s? And remember, the idea is that 2 electrons go in an orbital. And so as we might suspect, we need 1 orbital to house those 2 electrons. Now guys, before you draw this, notice the similarities and differences. This is the 2s orbital, and this is the 1s orbital. So how are they similar? Well, shape. They're both spherical. But then how are they different? And notice that the 2s is larger than the 1s, but you would expect that because we said that the energy level number tells us the size. So the 2s is bigger than the 1s. So what you're going to do is you're going to draw up and down, left and right, in and out, and then draw a sphere, but it should be bigger than what you did in the 1s sublevel. So let's take a second and draw that in. Press pause if you need. But let's go ahead and get that drawn. Okay, now that you've had the opportunity to draw that in, what we need to do now is we got to talk about these 6 electrons. So there's 6 electrons, there's 6 electrons in the p sublevel, but these electrons need to be in orbitals. So how many orbitals would it take to contain those 6 electrons? Well, if 2 electrons go in an orbital, that means that we would need 3 orbitals to house these 6 electrons. And sure enough, there are 3 p orbitals, but you'll notice that they are not spherical. They are actually figure 8, or many times we call them dumbbell shaped. And so what we're looking at here then, and you could certainly draw this in, we've got one that is up and down, we've got one that is left and right, and we've got one that is in and out of the board. So while it doesn't completely look like it, it's hard to draw three-dimensionally on a flat board, because what you need to understand is that these are 90 degrees to each other because of repulsion. Up and down, in and out, left and right. So go ahead and draw in those three orbitals, remembering that in each one of those, here, in each one of those, here we go. In each one of those, here or here or here, we have space for 2 electrons. So now that you've had the chance to draw those, and certainly you could pause if you needed, now that you've had the chance to draw these, again, find them in the room. And again, if you look front left, you will notice that you see these orbitals represented in that yellow-green in the front left corner of the room. So we still see the 1s, the smallest yellow sphere. Then to the right, we see the 2s and the 2p. The 2s is the larger yellow sphere, and then below that is the 2p. And you'll notice that the p is the bringing together of all 3 of those orbitals, up, down, left, right, in, and out. You can see that they're oriented 90 degrees to each other. But the other thing that's interesting to notice is that the p's are the same radius. They have the same radius as the s. The p is a little bit bigger, but not much. The size of the 2s and the size of the 2p are basically the same size. Okay, so now let's bring this together and let's really have the moment where we can connect this to what's on the wall. So guys, notice where we are. We have 2 electrons in the 1s, we have 2 electrons in the 2s, and then we have 6 electrons in the 2p. That adds up to 10. And if you look up at the periodic table, either on your desk or on the wall, you'll notice that element number 10 is neon. So if we take the 2 electrons in the 1s, the 2 electrons in the 2s, and the 6 electrons in the 2p, and we bring them all together around the same nucleus, that will give us a representation of what neon looks like. So guys, let me introduce you to neon. This is our best representation of what a neon atom looks like. Notice right here, we have an orbital, the 1s orbital. Notice here, we have a second orbital. That would be the 2s orbital. Notice it's the same as the 1s in that it's a sphere, but it's bigger. It's the 2s. Then guys, notice what we've got here. 1 and 2 and, this one's a little trickier, 3 orbitals. And these dumbbell-shaped orbitals are the p orbitals. They are the 3 orbitals that make up the 2p sublevel. Now guys, notice that the boundary of the p out here is a little bit bigger than the boundary of the s, but they're close enough that we think of them as being in the same energy level. So guys, bringing these all together, this gives us a much better understanding of how a neon atom looks, but importantly also how it behaves. And we're going to be talking about that as we move forward in this unit and then the next. Okay, so now that we've had a chance to bring together these ideas of orbitals around the same nucleus and how that lends to our understanding of electron structure, we now need to go back to our class notes. Now guys, glance back at your class notes just really quickly right now. And then turn your attention to the screen. How is the screen different than your class notes? And you'll notice the difference is the pictures are now gone, and now we have boxes and arrows. So guys, this is the idea. This box right here represents the 1s orbital, the sphere. So this is a small sphere. Now it's a little big. It's going to be hard to draw. So that box is a small sphere. This box is a bigger sphere, and then these three boxes are the dumbbells. But the idea here is that instead of drawing the shapes, we draw boxes. The reason that we draw boxes is that's clearly not the shape of an orbital, so people don't get confused. But then the question is, what are the arrows? And guys, the arrows represent the electrons. And you'll notice that the electrons have an arrow up and an arrow down. That represents what we call their spin up and spin down. But it is really representative of the direction that the north poles are facing. Now, guys, you're going to be drawing a lot of arrows and a lot of boxes. So let me share some tips. For example, if you want to draw an s orbital, we'll draw a box. But then, guys, the easiest way to draw arrows is check mark like this. Then, say that you want to draw a p sublevel. The easiest way to do that is to draw a rectangle, then draw two lines that give you three boxes, and then into this, you can put your check marks. So guys, let's move forward, and let's continue to think energy levels, sublevels, and orbitals, but now we're headed up to the third energy level. Now the third energy level, from your notes, three sublevels, S, P, and D. But before you draw them, be very careful here. So the 3S goes down. The 3P is a little bit above the third energy level. But guys, this is the important part. The 3D is just below the fourth energy level. Just below the fourth energy level. So when you draw this, make sure that that top D, or that top, D rung is right below the fourth energy level. Now when we continue to fill this out, again we've established some rules. The S's are 2, the P's are 6. So the S's are 2, the P's are 6. Then, logically, how many have got to be in the D? Well, we need 18. We've got 2 here, we've got 6 there. Do the subtraction, that leaves us with 10. All right. Now let's talk about what these orbitals look like. So what would the 3s orbital look like? It would look like a huge sphere. Draw a box with 2 arrows. What would the 3p look like? Well, the 3p would be even bigger dumbbell shapes. But guys, we are going to draw 3 boxes and 6 arrows. Now, what do the d orbitals look like? And again, if you need to pause in order to draw in your boxes and arrows, do that. But now let's talk about the d sublevel. Through subtraction, we said that the d sublevel has 10 electrons. Remember that each orbital holds 5 electrons. Or each holds 2. So each orbital holds 2 electrons, and we need room for 10. So that means we need 5 orbitals. And again, guys, this is just simple math. But here's the beauty of it. There actually are 5 orbitals. These are the clover leaf looking guys. But guys, again, we are going to draw boxes and arrows. So I will pause for a second. Again, the easiest way to do this is to draw a long box with 4 lines and then your check marks. Like so. Okay, so now that you've had the opportunity to do the S's and the P's and the D's from the 3rd energy level, guys, again, find them in the room. And if you look front left, you'll notice that you've got the 3rd column, if you will. In the yellow, green, gray guy, you've got the big yellow sphere. That would be the 3s. Then you've got the bigger green p orbitals. Notice there's 3. And now, guys, below that we've got the d. That is all of those clover leaf shapes brought together. But also notice that the 3s, the 3p, and the 3d are about the same size. And they all together are bigger than the 2s and the 2p. All right. So now we're ready to go on to the last energy level that we are going to do in this fashion. And it goes like this. The 4th energy level, right? The 4th energy level, 32 electrons. The 4th energy level, drawing our arrow over, the 4th energy level has 4 sublevels, S, P, D, and F. But guys, look how this goes. When we do this, the 4S goes between the 3P and the 3D. Then we have the 4P, the 4D, and the 4F. So guys, why does that happen? Why does the S, the 4S, sneak in? Here, let me grab a color that'll stand out more. Why does the 4S sneak between the 3D below it? And the answer is because the 4S is simpler. It's bigger, but it's simpler. It's easier to form a larger simple sphere than smaller crazy cloverleaf shapes. And as a result, the electrons will go into the 4s and then later into the 3D. Okay, and guys, if you have questions about that, we can certainly talk later. Just understand that, make sure that you get this pattern in your notes. So now let's put electrons. We've got 2 in the S, 6 in the P, 10 in the D. Now guys, again, 32 total. We've got 32, we'll stay blue. We got 32 electrons. We've got 2 and 6 and 10 is 18. Doing that subtraction, we have 14 electrons in the F. So now guys, let's think about what these look like. So what do the 4s look like? Well, it's a huge sphere. Draw a box and 2 arrows. What do the 4p look like? Even bigger dumbbell shapes. Draw 3 boxes and 6 arrows. What do the 4d look like? Even bigger clover leaves. Draw 5 boxes and 10 arrows. So guys, I'll pause for a second to let you get these all drawn. So now guys, if you need more time to draw your boxes, hit pause. But let's move forward. So now we're looking at the F sublevel. 14 electrons. I'm suspecting you can imagine that this would take 7 orbitals to hold those 14 electrons. Now, guys, the magic of this is that we came to that number, 14 electrons and 7 orbitals, by doing some pretty simple math. We've got the 2n squared rule, we've got logic, we've got subtraction, we've got division by 2. And guys, by doing that, we figured out that there should be 7 orbitals. The magic of this is there are 7 orbitals. And guys, obviously you don't need to draw this or write this out. But guys, it's amazing to me that there are 7 orbitals. Like, quantum theory is the most ridiculously complex way of understanding the world that we have ever come up with. It's the closest that we know to reality. The shapes are beautiful. And yet at the same time, we just figured out how many of these beautiful shapes there should be by doing the 2n squared rule, by subtracting, and by dividing by 2. That's pretty crazy. But in either case, guys, what we're going to do is draw 7 boxes and 14 arrows. So let's pause for a minute, and let's give you a second to draw in your boxes and your arrows. Okay, so guys, now that you've done that, this is where we are going to finish up today's conversation. Because the last thing that we need to do is we need to talk about the extra credit. So as you look at this thing on the wall, which is also on your notes, you know that this is a sphere, and a sphere in figure eights, and a sphere and figure eights, and a sphere and clover leaves and figure eights and clover leaves and whatever on earth we're going to say to describe those. But guys, we also know that they have different sizes. Their shapes are different. Their sizes are different. So should you choose to do the extra credit, this is what you will do. You are going to represent these boxes. You're going to take these and you are going to represent them in a visually accurate way. Now guys, understand when we say visually accurate, we mean by shape and size and by number of orbitals. So guys, for example, what might that look like? Well, a great example of that would be in the front right corner. Well, the front left corner. Guys, notice that we have these orbitals, and they are, correct. And they are correct by shape. The yellow guys are spheres. The green guys are the P's. They're the dumbbells. The D's are the gray ones. The brown guys, all the F's put together. So they're correct by shape. Notice that they are also correct by size. As you move across the S's, they get bigger. 1S, 2S, 3S, 4S. The P's get bigger. 2P, 3P, 4P. The D's get bigger. 3P, 4P. You get the idea. But guys, importantly, when you look within the energy levels, the columns, they're the same size. The 2S and the 2P are the same. The 3S, 3P, 3D are the same. The 4S, the 4P, the 4D, the 4F, they're the same size. Then guys, you'll also notice that they are correct by numbers of orbitals. There's 1S, 3Ps, 5Ds, and 7Fs. So all of those are present. So guys, the thing that you have to understand is this. while there are a lot of examples over here on the wall of extra credit projects, guys, very, very few of these extra credit projects got full credit. The one that we just looked at in the front left corner, that one got full credit. But very few of these did. So guys, understand, these are not meant to be models. Some of them I kept just because I kind of thought they were good looking. But it doesn't mean they're right. So guys, let me show you an example of one that didn't get full credit. I'm placing this, well, where can I put it that it won't be in the way? Let me see. Yeah, that'll be okay. So guys, I'm placing this in front of the Lifesavers. This is one that was done by Gracie Grover and Emmy Clark years ago. And it was good, but they didn't get full credit. So guys, why did they not get full credit? Well, let's go through this. So do they have the right shape? Well, yeah, the S's are spheres, the P's are dumbbell shaped, the D's actually have all the lobes. Pretty sure the F was right. I didn't really count that closely. But we're good on shape. Now what about numbers of orbitals? There's one S, there's 3 P's, there's 5 D's, 7. Okay, so we're good there. Guys, it was size that they got wrong. Take a good look. If you look at the S's, from purple to green to orange to white, do they get bigger? They do. If you look at the P's, from the green to the orange to the white, they get bigger too. So where is the size mistake? And the answer is within the energy levels. So the green guys, the 2S and the 2P, should be the same size. The orange guys, the 3S, 3P, and 3D, should be the same size. The P and D are, those are out of order. Well, you didn't know that. You can't see this. The P and D, they're back in their right place. The P and D are pretty close to the same size, but the S is way too small. And so, guys, understand that to get full credit for this, they need to be right by size, shape, and number of orbitals. So, guys, there's 2 other things that you need to know about the extra credit. Number 1, you're welcome to do this with a partner. Just 2 of you, could be alone, up to 2. And that person doesn't need to be in your class. They also don't need to be in my classes. They could be someone from Ropers as well. That's fine. But guys, also, in order to get full credit, your project needs to be original. And by that I mean, I shouldn't be able to look at the wall and go, wait, haven't I seen that before? So guys, let me give you an example of this. So we've obviously been looking at the model that's at the front left of the room, the one with the yellow, green, grays, and browns. But if you look at the back of the room, you'll notice in the northeast corner of the room, there's another one there with circles and, well, you see. So both of these got full credit. The reason is because while they are similar, the one in the back was done with paper, and it's very much two-dimensional, well, for part of it. But then the one in the front was done on a laser, on a 3D printer, and much more accurate. So the one in the back was done first, gave them full credit for that because it hadn't been done before. And the one in the front I gave them full credit for because it took the idea of the one in the back and extended it. So guys, understand, while all of this doesn't need to be completely like, oh my gosh, like never, well, let me say it differently. You can take an idea and extend it, but you can't copy it. And so if you're not sure whether or not your project would receive full credit, I'd love to talk with you about it. And guys, finally, these are due the day after Thanksgiving break. So if it's an A day, it's due on the A day after Thanksgiving break. If it's a B day, it's due on the B day after Thanksgiving break. If you're doing it with another person and you're in different classes, you can turn it in either time. So guys, thank you. Thanks for tracking along. I hope you found this interesting. I'm always compelled by the idea that we can do simple logical thinking and a little bit of math, and we can figure out all these crazy structures up on the wall. So what we're going to do for homework is grab your homework packet, and homework assignment number 2, the answers are on the wall, but only the front of the assignment. And guys, importantly, question number 2 says, write out the orbital filling order for an atom's electrons through energy level 7. Guys, don't go through energy level 7, go through 4p. That's as far as you're going to get right now. So just go through the 4p. And then from there, we'll get together and talk more. So guys, you're going to do that. It shouldn't take very long. If you want to start strategizing about your extra credit projects, that would be a great idea. Also, and this is specific to you guys on Tuesday, you probably have heard, if you haven't, that class is called off on Thursday because of the football game. Guys, understand that we will restructure the calendar. I am not going to have you learn this stuff from home via screencast. That's not right. So when I see you on Monday, a week from now, when I see you on Monday, we will get together and we'll talk about how we're going to go from there. Guys, we've got another day to really fine-tune this and tie it to the periodic table. We'll do that when I see you on Monday. So again, guys, on Monday, what we'll do is we'll turn in the homework that we should have turned in today. That was the stuff with Heisenberg and probability and that stuff. Then, guys, we'll turn in the front of homework assignment number 2, and then we'll go on from there. Guys, understand we also have a problem relative to remediation, because the remediation, the essentials test was supposed to be on Thursday. We will move that to Friday, and it will be Friday before or after school. So guys, please don't get lost in all of this. If you need any support, drop an email, or just understand I'm not here Thursday, but I'm here the rest of Tuesday. I'm not here Tuesday or Thursday. Holy smokes. But guys, please reach out if you need anything, and I look forward to seeing you all on Monday.